Okay, welcome back. We're talking about abstract machines. So once again, this is a thought experiment. They're not real. And they envision like a machine with a paper tape with symbols on the tape. And the machine could read the symbol and then figure out if it wants to output it or do something to it. And so it has to have some way of determining what it's currently processing. So in our example here of parsing words, I need to know, am I inside a word? Am I inside a run of letters that make up a word, or am I inside a run of white space which does not make up a word? So I have to maintain some state of what am I currently processing? Am I currently looking at a word? Or am I currently looking at white space? So that's what that is. Okay, an automaton is basically just an extension of that. Automaton is an abstract machine, but with the ability to transition from one particular state to another. In other words, not only does it see the states and know the states that it's in, it changes its operations. So, for example, if I'm in the, hey, this is a word state, I need to be storing those letters, don't I? I need to be storing the M and the A and the R and the Y. But when I get to here, I've transitioned to another state. I don't need to be storing anything here. So that's what an automaton is. It's all it is just an abstract machine that has the ability to transition between states. Cool. And for it to be an automaton, you really need to have a finite number of states. I mean, you can't just say, well, I don't know how many states there are. There are maybe a couple hundred. No, you need to tell it exactly how many there are, because when it comes time to implementing one of these, oh yes, we're going to do that in a homework assignment, you need to know how many states there are. In this case, it's pretty simple. You're either in a word or you're not in a word. Okay? That's you could, I'm going to call that two states. But when it comes down to programming it, I'll probably just use one variable that says yes or no, right? A Boolean. So one state, but I'm only going to, two states, but I'm only going to consume one variable. Okay. So let's go a little bit further. I'm going to go ahead and just show you one, because I don't want this entire chapter to be completely hypothetical, okay? So let's just go through what it would take to make one of these things work. So here we go. So here I have an application, and it reads a poem, and it's Mary Had a Little Lamb, but I threw in a new line and a handful of spaces here just to kind of make it more complicated. Now, if this is an automaton, then what I need to be able to do is I need to be able to read this thing one character at a time. One of the rules for this automaton is you can't fast forward on the tape, and you can't reverse the tape. The tape runs at one speed, and it runs one character at a time. So that means you're going to have to be able to read this thing one character at a time and figure out what's going on. So my state that I'm in is, am I in white space or not? So I did that with one Boolean character. And I have another state here, which means where is the start of the word? I don't actually need that, but I threw it in just for the heck of it. So let's start. So look at each character in the poem. Javanauts have to do it this way, but I'm just going to say the character is equal to whatever thing. And then I'm using a switch statement, which is an extraordinarily simple way to do this. I'm hunting for white space. So white space could be a space character. It could be a tab. It could be new line. So if it's one of those things, that I'm definitely in the white space mode. But if I already have a word, if I already have something stored, okay, then it's time for me to display that thing and skedaddle. In other words, once I hit the first white space, I go stop. I want to transition to another state where I'm now done with the word, right? And therefore I want to display, I don't want to display the space character, I just want to display the word. Now, there's a thing called a push down automaton, which means you store these things in a stack. Whenever you see a letter that's a valid letter, like M for Mary and A for, you would put it in a stack. Look, you can use a stack, you can use a queue. I chose to just use a string buffer, okay, just to make things simple. So I go down to here. And so if it's not one of these things, then I know that it's a legitimate thing. So if the previous character was a white space, well, then I start over with a brand new word, and therefore I add, this is my buffer, so I could use a stack or queue, but I chose to use this, and then I spit this thing out. Now, I'm going to go ahead and show you a preview of the next. So this is code you have to write. But the next lecture, we're going to use a practical implementation of something called regular expressions. And that's the symbol I'm after. It's a W plus. W means word, and plus means more than one. I'll take more than one of them. Or if I put an asterisk, that means one or none. Here I put, no, I want at least one. Okay, so that's what that W plus means. And then I basically just go in and use this thing and then spit out what I want. So I'm going to run this just to show you what it looks like. So by using my technique, I figured that the parsing this by words, I came out with Mary had a little lamb, its fleece was white as snow. So that's the technique. Now, one more time. This is a push-down automaton. That because it stores information, it maintains state. Now I did mine with this an extra helper. I didn't actually need that guy. I could have left that guy out, but I just kind of did it as just an easy way of determining whether or not you're actually inside a word or not. I could have just asked for the word length. You know, does my buffer contain anything? Yes or no? That would have been just as good. It's just that, I don't know why I did it that way. I just thought it would be a smart idea. Okay, so now let's go back to the honest-to-God automaton thing. Parsing things into Word is an example of an automaton. One more time, what are the rules? So in a push-down automaton, which we're going to be talking here about in just a few minutes, the rules are I need to read one character at a time. I need to be able to maintain state. I need to be able to transition from ignoring the input state, like words, space, white space, to oops, I need to be collecting the state. Push-down automaton technically requires a stack, but I'm not going to require that. You could use a stack or a queue or just a string buffer like I did. Okay, good. And you need to handle what happens at the end. What I'm saying here is words are delimited by a white space, but not at the end. So I have to have an extra little thing down here that says, hey man, if you still have some stuff, then you need to spit it out. So I have to have a special case that's after this entire loop is done. After the loop is done, I have to say, wait a minute, do you have anything left in that word buffer? Because the starting and ending ones are different. Everyone else is separated by a white space, but not the start and not the end. Okay, good. Whew. Okay, so there's different types of automaton. Back to the lecture. One that accepts a language, and then the task of your automaton. I'm going to close this because that's not what we're talking about anymore. The task that your automaton may be asked to do is this word in the language? And so it would go through and check. So the answer there would be yes or no. Right? So that would be a finite automaton, wouldn't it? I know what the answer. It's only one answer. Okay, good. The other one is like where I have to do some computation, where I do some input and do some output. Let me give an example of a computational automaton. Let's say I wanted to write a program that could evaluate this. Let's do 8 plus 4 times 2. Okay, I want to write an application that can take that and tell me what the answer is. So you're reading it, you say, okay, I got an 8. Okay, I'll store that. Well, I got an operator, a plus sign, I'll store that. I got another number, I'll store that. I got a star, asterisk, and I go, wait a minute, that has higher precedence than the 4. I cannot do the addition first. Right? Remember how the grammar would require certain things to happen in a different order? So this is a computational automaton, where behind the scenes it would have to go in there and go, well, no, wait a minute now. We really kind of sort of have to do this one first before we do that one. And then when we're done, we're going to end up with a numeric answer. So that's a computational. And then there's one the type, deterministic versus non-deterministic, which means clearly a deterministic one would be one that I know exactly it's going to come up with an answer, and it's typically, you know, only one outcome, or perhaps different scenarios would come up with something different. The English language is really, really funky. I mean, geez, right? There's an awful lot involved in this thing. And so I would consider it a non-deterministic, because if you're trying to check to see if two sentences are essentially equivalent, wow, man, that is tough. Okay, so let's talk about this one more time. I'm trying to give you real-world examples that let's say your job was to count the number of sentences in a Word document. Okay? You would think that would be finite. There would only be one answer. And you think it'd be deterministic, which means I'm always going to get that answer. I mean, it's not like you're going to go off in Never Never Land and come back. So this would be like a computational automaton. But let me just show you how complicated this could be. First of all, what is a sentence? Well, a sentence in the English language is going to end with a dot, or a question mark, or an exclamation. So you go, oh, well, that's easy. All I'll do is just count the number of those things, and I'm done. No. What if I said, Dr. Jones is teaching CIS4340. How many sentences is that? So does a sentence always end with a dot? Wow. No. Okay, let's do another one. She asked, what time is it? And I said 2:30. So, does a sentence always end in a question mark? Oh, no. So, in this particular case, one of the states that you would have to maintain is, am I inside a set of double quotes? That would be a good one. So, because if I find a dot, period, or exclamation, or a question mark inside a set of double quotes, I'm not counting that as a sentence. See how this could get really, really complicated. Now, I'll confess, back in the old days when we had two spaces after the period, that would actually help a great deal, wouldn't it? Because here you would always have like one space, and then over here you'd always have two, right? Unless it was like at the end of a paragraph, and then you wouldn't have any spaces after it. So yeah, can you see how this could get complicated? Yes. Can you see how computer science people have to write programs that parse a given input like this? You need to be able to parse that. Or let's say you're writing a database and you need to be able to parse this into tokens. Right? You need to be able to figure out, is that right? Is it in the right order? And then what do I do? Okay? So yes, this is a heck of a lot of stuff that you have to learn. Okay, on page 153, they talk about the simplified grammar example. So this is clearly simplified, but let's just say that sentences start with and have some sort of a noun and some sort of a verb. And then nouns have an article or an adjective or a noun, or perhaps just an article and a noun. And then verbs could have verbs or adverbs, or just plain old verbs. And then articles could be a, and, or the, and adjectives could be those guys, and nouns could be those. See how this thing works down? So, are all sentences made up of all the components every single time? Well, of course not, right? So just kind of think about this. If you were tasked to parsing English using these set of rules, how would you go about doing it? And of course, we're coming up on the 15-minute mark.